I want to start my talk with a disclaimer. So I have a lot of jargons and keywords in my title, things like IoT, neurofeedback, sleep monitoring, gesture recognition. Most of this is for show. However, there are two main goals of this talk. The first goal is to present the methods that we use in our lab to develop IoT systems. And the second goal is to show the diverse set of applications that such research methods could facilitate. So what do we do in the lab? We mostly try to innovate in hardware design, sensor design, underlying signal processing algorithms that take data from the sensors and make meaning out of them, overall system design, as well as feedback from humans. So in our lab, we have developed several novel sensors, which includes textile capacitive sensors built into clothing, micro-Doppler radar-based sensors for motion detection, physiological sensors for determining heart rate and heart rate variability. These sensors integrate with mobile systems to collect data, and then we build things like signal processing algorithms and analytics on top of the data to make meaning out of it. But a lot of systems do that. One of our core novelty is actually making sure that we have the human in the loop. So most of the systems that we do develop are used by humans. And we believe that not only the sensors should understand the humans, but the humans should also understand the sensors. So we use different techniques like physiological monitoring, real-time physiological monitoring, even brain waves monitoring, to understand what the human is thinking about the sensor, that the human is actually learning the sensor. And then feed that information back, both in the hardware design as well as the underlying signal processing algorithms. So such an approach can actually enable a large number of novel applications. We have built applications for gesture recognition, mostly gesture recognition for people with limited mobility, people with paralyses. We have used sensors for tongue gesture recognition. We have used sensors for whole body monitoring during driving to understand whether somebody is actually driving drowsy or drunk. We have used similar sensors for leg movement monitoring during sleep and figuring out what the quality of sleep is, as well as whether you are actually prone to sleep-related disorders like attention deficit. In collaboration with the Army Research Lab, we have been looking at ways through which we can provide visual neurofeedback to soldiers to improve their performance in the field in high-stress conditions, for instance, in a shooting task. And finally, we have been also looking at ways through which we can use similar techniques in cyber-physical system security. One of the things that we have been looking at in security is not necessarily inferring if there is going to be an attack, but making sure that the system gracefully degrades even in the presence of an attack. So if there are sensors compromised, can I make the system actually still work? And that's extremely important, especially when you're dealing with industrial control systems. So what I've done in the rest of my talk is kind of delving deeper into each of these applications, showing you some pretty pictures and videos to demonstrate how this particular research method is actually applied in my lab. We talked about wearable sensors. So one of the things that we have been developing over the last 3 or 4 years is these textile capacitive sensors, which can be embroidered into your clothing. So these are very small sensors that are kind of invisible from you and would be part of your clothing. So essentially, they detect motion, but they are very fine-grained motion detectors. Just think of it in terms of multiple computers looking at the motion from different vantage points and giving you very fine-grained resolution on the type of motion that it can detect. And these sensors can potentially be embroidered in your items of daily use. Once you have a sensor like this, What you could use it for is to understand things like body language. So what you're doing, what you're interacting with, et cetera. And at the same time, such sensors can be used for gesture recognition, which could be used as an input modality for environmental control. This is especially important in a particular population group, the population group which suffers from paralyses. These folks have very little mobility, but very subtle motions. And those motions could potentially be used as input in our system for things like making a nurse call, making a 911 call, or even like controlling your appliances. So what I have out here is actually a video of our system working with a C5 spinal cord injury patient. So he has the pad on his thigh and is essentially performing the gesture. The gestures are actually being recognized on the sensor itself, and it's tied to a home automation system, which is controlling that fan. And at the same time, that we have built a 3D visualization interface using Unity that real-time collects the data and shows the user how the system is understanding the gestures. In another experiment, we actually had a headset, which is an EEG headset, on the patient to really understand how he's learning how to use the gestures. So one of the key elements of this gesture recognition system is that it's highly personalized. You can potentially perform gestures in different ways, small gestures, jittery gestures, and the system would actually learn what that gesture looks like. So the type of gestures that are performed by different people with different type of spinal cord injury is very different. So the system should be able to learn and adapt based on the user, and our system does that. So for folks with very severe paralyses, like higher level spinal cord injury, we have developed a non-intrusive tongue gesture recognition system. So most of the tongue gesture recognition systems that are out there are intrusive. You have actually got to place some sensors inside your mouth to detect the tongue movement. We have been using the same sensors that are used in your cars to detect collision, the micro-Doppler radars, to detect very subtle movements of your muscles when your tongue moves in different directions. One of the prototypes that we developed was actually as a part of a helmet, where we have an array of these micro-Doppler radars that can detect different types of tongue gestures. And again, the idea here is once you are able to actually see these gestures, you can use them for a lot of applications, like using it for environmental control. Similarly, the capacitive textile sensors built as an ankle band could be used for detecting specific leg movements during sleep. What we have shown is certain leg movements during sleep have correlations with microarousals, which are periods of times that you wake up, but you don't remember that you have woken up. This causes fragmentation in sleep. So when you wake up, you're tired, but you don't necessarily know why you're tired. Usually, this sort of an analysis is done in sleep labs using EEG headsets. So we want to potentially transition a lot of these things that are done in labs and are expensive to the home. I have a video here, again, of our system in action. What our system does is it detects foot flexions and distinguishes them from general leg movements, which are movements of your leg when you move around in your bed. So these foot flexions, which would be shown in a minute, these ones are involuntary. And they are correlated with disease states like attention deficit in kids. So their frequency, for instance, could be matched with how severe your RLS or ADHD is. And these general leg movements are actually correlated with texture of sleep. So things like sleep fragmentation and poor sleep quality. So our system collects these sensors, sensor data, distinguishes these two types of leg movements, and then applies machine learning techniques to determine whether certain leg movements are actually correlated with either insomnia or sleep fragmentation. So another example of a system where we are not only building the hardware and the signal processing around it, but the analytics on top of it to provide feedback to the user. So we have all the jazz with the web dashboard, et cetera, for doctors to look at. And we've spun off a company on this, which is commercializing this particular product. Another application of these sensors. So you could potentially build these sensors also into car seats. Unlike cameras, which have a limited view of your body when you're driving, these inexpensive sensors can be used for whole body movement detection. And you can correlate these whole body movement detection with things like drowsy driving or distracted driving or fatigue driving. So we've actually deployed this in cars to see if we can potentially use these movements to correlate with poor driving. Another application that we have been looking at with the US Army and the Army Research Lab is ways through which we can provide neurofeedback to improve the performance of soldiers in the field. So these are very high-stress conditions, like a shooting simulator, where the person is performing a task, is stressed out. How can I essentially provide some sort of a feedback, both visual or auditory, in order to improve their performance? We have been collecting over the last couple of years a very rich data set where users come to the lab, perform these tasks, and in addition to collecting things like information on where they are shooting, eye tracking, et cetera, we also collect a lot of data on things like EEG, EKG, respiration rate, real-time blood pressure monitoring, et cetera, as well as subjective data on stress and anxiety. So a data set like this could enable a lot of research. For instance, we are looking at ways through which we can better understand correlations between respiration rate and coupling of respiration rate with heart rate. So it's called cardiovascular coupling. We've also been looking at ways through which brain networks are essentially created as these certain tasks are performed using more nonlinear approaches like structural synchrony. So in addition to building sensors and actually deploying them in the wild, one of the things that we have been doing in our lab is collecting these very rich data sets which could enable research just on the data of this granularity. We have set up a lab in the Technology Research Center where we have spent a lot of time building systems that can collect very fine-grained, very finely synchronized data across these different data sources. Additionally, we have also been looking at ways through which we can kind of tackle the cyber-physical system security problem. There are lots of solutions out there which would look at inferring whether there's going to be an attack or not. What we have been looking at is ways through which we can make the system still operate, even in the presence of attack. And we have been using a cross-layer approach for that. So at the sensor level, we have been using side channel analysis, power analysis mostly, to kind of reverse engineer if the firmware on the sensors have been mucked with. So what that provides is hints on how trustworthy the sensor is. And at the higher level, what we have been looking at is more distributed systems algorithms like trusted consensus to determine if we can aggregate information from multiple sensors in a weighted way, such that the data that is actually fed back to the actuator is still useful. So what we have found is, even if a large fraction of the sensors are compromised, using such a cross-layer approach, we can potentially get data into the actuator which is meaningful. So which makes the system still run at some level, even in the presence of attacks. So again, the goal is not necessarily to determine when the attack is happening, but make the system run in a graceful way, even in the presence of attacks. This is especially important in industrial control systems, where you don't want the system to shut down, like when there's an attack. You still want it to operate at some level in the presence of attacks. So I wanted to reiterate back this research methodology slide. Almost all the applications that I've been talking about deals with development of novel hardware, analysis of data from the novel hardware. The mobile system component may or may not exist. But there's usually a human component to the system. And what we are trying to do in all of these systems is kind of tune both the signal processing algorithms that we are developing as well as the hardware that we are developing based on feedback from the user. So we really want systems which, A, understands humans, but we also want to understand how the humans understand the sensors, so both ways. So I will stop with that. So most of our work is part of this particular cluster group called Eclipse. And this actually includes faculty members who have expertise both in hardware design, signal processing algorithms, as well as data analytics. So it's a very collaborative effort. Thank you.